So can everyone hear me? Is all right? Perfect. Yeah, so I'm Rory. I'm a fourth-year PhD in the computing science department as part of the computer vision and autonomous systems group. Today I'm going to be talking about some of my recent work, which was published at NeurIPS, focusing on chaos in deep reinforcement learning. There we go, good. So hopefully over the course of this presentation, you'll be able to understand how we can use machine learning for controlling these sorts of systems, some of the benefits of this, and some of the challenges applying it towards more realistic sort of scenarios. So to start off with, a little bit of formalism. This control interaction is represented by the Markov decision process. It's a feedback loop containing two elements, the environment and the controller, also known as an agent. Example environment on the right. Every 100th of a second, the environment will produce a state. This could be an image, but I've been working with lower dimensional vectors. So this could be cart position and velocity, or the angles of a more human-like robot. This state is passed to the agent or controller, which then has to decide an action to apply back to the environment. It could be moving the hip angles or moving left or right. With this state and action, the system will then transition to a new state, as you can see on the right-hand side. And then, in addition to this, you'll get a reward. It's a value telling you how good or bad your current state or action is. For this system, it's called Walker. I work with it quite a lot. It gets high rewards if it's standing upright and walking forwards, but it gets pretty bad reward if it's falling on the floor. So the overall goal of reinforcement learning is to interact with this control loop, collect examples of states, actions, next states, and rewards, and then train a policy called Pi, which maximizes the total reward over an episode. Importantly for this, we don't know explicitly what the transition function is, so how the states progress to the next states, or what the reward is. All we can do is interact with the system and collect examples of states and actions, next states, and rewards. So that's the general framework. A lot of different methods can be used to maximize this total reward. One I've been working with closely is called Dreamer. It is a model-based method, so it learns the transition function and reward function, the two things we don't know. It does this by sampling example states, actions, and rewards. It'll then use an encoder and decoder to try and compress this into a latent space, and it'll then use a recurrent model to try and predict the next latent space. And then we can do it again. And if you give enough examples of state trajectories with actions and rewards, it can do pretty good predictions. So we've given it the first 5 frames as context, and it can predict pretty well up to about 30 frames into the future, at which point it starts to diverge, most likely due to issues with model prediction. And then, to train a policy, it uses this learned dynamics model, which we now know and understand, to produce actions which maximize the total reward. So the objective for the policy is to maximize reward. And initially, without any training, it doesn't do much. It just falls on the floor. With some training, it can learn to walk forward, still stumbling over a lot. And with lots of training, it can eventually learn to stand up, walk forwards, and it maximizes this total reward for doing these two things. Now, these systems, during deployment, are deterministic. So if you start in the same initial position, you will always do the same thing. So I've got about 40 robots here, all with the same initial position, all doing the exact same thing in this simulated world. There we go. Now, what I've been looking at is what if they don't start in exactly the same position? but instead approximately the same position. So I've made a small change. It's so small you now can't see what the change is. And I've also shown the torso height and the torso angle, the two things we use for reward. And if I hit play, we can see initially these systems do the same sort of movement, but after about 100 steps, this single small change has had quite a large impact on the overall system. What's more, if we look at the total rewards, this value we've been trying to maximize throughout training, then for the most part, it's getting about 500, which is the maximum it can get, is what we expect. But there's small changes we can make which make the reward go right the way down to 0. And this single small change has had a large impact. Yeah, so it has a significant impact on the overall performance. So this high sensitivity to initial conditions, what's going on? Well, it's creating a chaotic feedback loop. In reinforcement learning, all that's really cared about is maximizing reward, which doesn't really translate the best to real-world systems where you want more guarantees on stability. You don't want this small change, large impact. So we can measure this sensitivity using a metric called the Lyapunov exponent. We essentially make a small change, progress this system forwards, and then see how quickly these systems diverge. Formally, it's these two equations, but broadly speaking, if this value is negative, the system's stable, as it will converge despite this small change. And if it's positive, then it's chaotic. So for 6 of the systems available, we've trained a bunch of, we've trained 3 different reinforcement learning methods. And we find there's broadly 2 categories. The cart pole, which is a simple carts on a track with a pole attached, generally produce stable dynamics. Whereas the more high-dimensional walker and cheetah produce quite chaotic dynamics as they've got positive MLE. And this basically means that if you have an approximate observation, you can't predict long-term dynamics. So, easy to show this. How do we solve it? Well, what I've proposed is an extension to Dreamer, where instead of making one future prediction, we make a series of future predictions. Now we've got a few H2s, a few different predicted states. And then during training, as well as maximizing rewards, we want to minimize the internal state divergence, this, the difference between the predicted internal states and the predicted states. And so depending on how much we value maximizing rewards versus maximizing stability, we get a trade-off where we have more stable, higher performing, less stable policies, or lower performing, more stable policies. It's quite a nice trade-off curve. And so these policies, what do they look like? We've learned to straighten our leg and march forward. And my personal favorite is learned to do the worm. Apparently, it's a really stable policy. It's still upright for some of the time, still moving forward, just not quite as high performing, but it is more stable. So in general, 4 things we've learned from this: that the interaction between deep reinforcement learning policies and the environment can produce chaotic dynamics. This means it's impossible to actually predict long-term state dynamics given an approximate observation. You cannot guarantee performance because a small change can significantly degrade. And then to address these, we have proposed a regularization for state-of-the-art model-based method. So thank you very much. This paper was presented at Europe's, so if you're interested, the full paper is on the right. If we have time for questions, happy to answer any. If not, my email's here, and I can wait outside as well.